In this session, we're going to talk about some techniques for getting bugs out of an embedded application, and better yet, how to prevent them from happening in the first place. I'm Dave Nadler, and I've been building software and systems for a really long time, since 1973. I've worked on lots of different kinds of products, from tiny embedded things to very large distributed systems in both hardware and software. And I've worked for decades as a consultant, but also in some large corporations, most recently leading a team which topped out somewhere around 250 engineers. In addition to developing products, lots of my work has been helping firms get problem projects on track. These days I mostly consult on embedded products, and current projects on my desk here include test instruments, which are for different applications here used for semiconductor fabs, aircraft and jet engine manufacture, one here for some pharmaceutical manufacturer, and also some avionics research. When we start a new project from scratch, we use both test-driven design and test-driven development. If you haven't already done so, read James Grenning's excellent book, Test-Driven Development for Embedded C, and attend his workshop at this conference. Test-driven design is something a little different. Test-driven development is often explained from the bottom up. We do test-driven design at the system level, which means we define the system tests before coding. We do that first. And this really helps refine the system specifications and requirements. You must always remember that software that isn't tested is buggy. If you've got tests that are very hard to run or require lots of manual steps, they won't get run very often. And then you have untested software, which is buggy. Test-driven design and development reduces the net time to get to a shipping product. It seems counterintuitive because you need to spend a bit of time at the beginning of a project setting this up, but by the time the product ships, your savings will be quite substantial. We design for testability in both hardware and software, and this means including features to ease testing. By defining tests first, the tests tell us what we need to do to make the product testable. For hardware, the tests tell us what test points we need, debug connectors, status LEDs, test output points, pins that we need, things like that. For software, the tests tell us what mock and stub interfaces we'll need. A good example is a project sitting here on my desk, which provides an override for a set of sensor input values on the target, not just on the simulator. A simple script forces some sensor values and checks that we get the expected results. We build a simulator on the PC, and often before we even have prototype hardware. The simulator builds the application code as a PC executable. We're not using QEMU or anything exotic. We build into the simulator support for simple scripted testing so that we can replay a test, capture the outputs, and check for the correct results. Scripted testing is TDD. It helps for initial development, and then it helps prevent regressions as we continue forward through the project. Maybe we're going to use continuous integration on top of this, maybe not. But the most important thing is to have simple, repeatable, and automated tests. Good coding. We try really hard to use good coding practices, and that starts off by being incredibly paranoid. Every module or function has a set of assumptions about the environment and about the inputs provided. Use plenty of asserts to make sure that these assumptions are not violated. Be paranoid about resource use. Memory use, stack and heap, other resources. It's not enough to look at the application in the debugger and say, oh yeah, the stacks for each of my tasks seem to have adequate reserve space. It doesn't help you going forward. Build tests into the product to check and make sure of adequate heap reserve, and for each task, adequate stack reserve. And you got to be paranoid about other resource use, CPU, performance issues, buffers. As we're going to see in the example, for example, one thing that's commonly left out, check the minimum amount of excess space ever left in a buffer. If you get down to 0, that means you had an overrun, you had data loss. If you don't check it, you're not going to find out. Very simple but obvious. We always turn on all the compiler warnings and make sure that everything compiles without warnings, and that prevents a lot of unfortunate things from getting through. One of the most important things in any project is regular design and code reviews. Actually, any kind of engineering, not just software. I've introduced code reviews at a lot of organizations, and without fail, it can be difficult to get going, but once folks are in the habit, they don't ever want to go without reviews. It just makes things a lot less aggravating. It's less time-consuming and expensive to catch problems early. The cost to fix a problem increases as something like the square of the time between the coding and the fix. So doing reviews gives a net savings in time and cost to the shipping product because you pick stuff up sooner. We have a preferred toolkit. First and foremost, C++. We use C++ because we can build smaller, faster, more reliable code in less time with fewer bugs. And here I got to tell you a story. Very early in my career, the firm I was working for won a bid against a very prestigious competitor. And we later found out the competitor had told the customer, using C is ridiculous. Serious projects use assembler. We successfully delivered the project in C, and that was in the year 1977, if I recall correctly. And I am reminded of that episode every single time I hear somebody arguing we should be using C instead of C++. C is 70s technology, and really, we've been using C++ for embedded systems since the 90s. It's for over 25 years, and it really does help. FreeRTOS is a great tool. We've delivered lots of products with FreeRTOS and several different processor architectures. Use an RTOS and not a super loop to avoid lots of problems, and we're going to see some of those problems in the example we're going to cover in this talk. You've probably used WX widgets in plenty of popular tools such as FileZilla, Audacity, and KiCad. WX widgets is very easy to pick up, and it makes it really easy to build a simple simulation framework. So that's what we tend to use. In summary, we don't use these tools and techniques because they're cool and trendy. We use them because they really work. They reduce time, cost, and aggravation. We get stuff done sooner and with a lot less grief. And using these techniques reduces the time and cost to deliver a project. Well, it's all very well and fine to talk about what we do on a new project and how we prefer to approach things, but a lot of times we don't work on new projects. So the next question that arises is, what are we going to do when we're confronted with an existing project? When we're confronted with an existing project, we're often looking at something that is not built as above, and we have to figure out what we're going to do. Are we going to proceed heads down and carry on as the original developers did without any of these tools and advantages that these tools provide? Are we going to start to think about adding some of these techniques? If it saves time and reduces bugs, absolutely. And when I say saves time, it's, again, how long is it going to take us from start work to delivering what we need to deliver without bugs? The other issue is some of the bugs that are lurking are not going to be found easily or at all in some cases if you're only using the target platform and traditional techniques, as we're going to see in the example. So what we're going to do here is we're going to talk about a real example case which landed in my lap last summer, and we're going to see which techniques worked for which bugs. And this product is a very, very typical embedded product, coded in a fairly typical fashion. The example project we're going to discuss is a aircraft traffic display screen. This display shows traffic from the FLARM traffic and anti-collision product. FLARM is a very, very successful system which displays information about other aircraft equipped with FLARM. It was originally developed for gliders, but now it's used in the majority of general aviation aircraft in Europe or the EU, and probably 1,000 or 2,000 in the United States. It'll display alarms if there's a pending collision. I'm proud to say I was one of the developers of the PowerFlarm product, and there are now something over 50,000 FLARM units installed in aircraft around the world. So special thanks to the product's manufacturer also for allowing me to use this for this presentation, the product here. The product is a little display screen. You can see other aircraft, own ship, that's us in the middle, somebody close behind to our right and rear. The highlighted glider to the right is 8 Yankee. A little bit of information about altitude differential, climb and descent rate, distance. This product uses serial data input from the FLARM. The simple UI, again, you can press and twist to make selections. Pretty simple, standard kind of thing. It's a very successful commercial product. There's thousands in use. And it needed a couple of minor fixes and a small feature enhancement. The original developer wasn't available, didn't have time to work on it at this time. I had a bit of spare time, So I said, okay, I'll see if I can take care of it. But the first thing we got to say is what's an efficient approach to working on this. To figure out how we're going to approach dealing with the technical issues here, we got to look at the product. It's based on an Omega AVR processor, 8 megahertz, 8-bit RISC machine, quite popular for products developed in this era, used in several Arduinos. It's got 256 KB of flash, which is partitioned into areas for the bootloader, program database for aircraft identification and detail, and the program about 98% full. 8 KB of RAM, mostly full. EEPROM storage on chip for some options. It's a bare metal, no RTOS. Uses C AVR GCC, which is a 16-bit integer, despite running on an 8-bit RISC. Around 18K of source lines, less than 1K of platform-specific driver stuff. The source line count includes things like font tables, so it's not really a very huge program. How to debug it? That's an interesting question. Okay, it's got ISRs for serial, knob button, and the time base. But other than that, not too much platform-specific things. SPI interface to LCD. Open source drivers for the serial port and the LCD. No easily accessible debug probe connector, so I've got a few of these things, but there's would require a fair bit of surgery to get a debug probe connected, even though I have a debug pod in my junk box here. Again, the platform-specific stuff limited to ISR, serial driver, and SPI code. Another consideration for figuring out how to work on this thing is it's not really a wonderful IDE available for this particular platform. We get spoiled with modern development tools like Eclipse with well-supported, J-Link debugger over SWD into ARM. This vintage, the stuff was not quite so nice. Let's review the objectives for this project. The firmware needs a few small modifications, and as we say, how hard could it be? First, we need to add a small feature. It's just going to send a command over NMEA to the FLARM and capture the response and pop up a dialog confirming that the action that the user requested was taken successfully. Then we need to update the serial protocol for the FLARM. The serial protocol has been updated a few times, a few revisions since the last time the firmware in this product was updated, and it's been suggested that this has been possibly causing some of the problems that have been seen with the product. A bit more worrying, a lot of reports, the product seems to be a bit flaky. One of the menu options disappears after the product's been operating for a while. There's some screen artifacts and no proper bug reports, but scattered imprecise complaints about flaky behavior. And this kind of thing is a bit worrying. So what approach to use? How to approach modifying the firmware for this thing? What is going to be the quickest way and the least cost path to finish? The default is to kind of keep hacking away at it on the target hardware the same way that the original developers did. I have the debug pod, but even if I had it set up and the IDE is all ready to go, it might be a bit hard to track down some of the flaky problems on the target hardware. One of the first questions we ask is, should we simulate this on the PC or not? The existing software had no PC simulator, so should we build one? Debug cycles on a PC are much faster than build and reflash cycles using the embedded target. Even with a modern, fast debug probe, it takes a bit of time, and we have only an older, not-so-fast debug probe. When you're using a capable PC IDE, it makes it a lot easier to learn the unfamiliar code base. Good IDEs these days provide lots of facilities to help. They integrate with source control. They help stepping through code to see what it's doing a little bit more easily than you do on the target hardware. Searching for references. All in all, things just go faster with a more capable IDE. The GUI on this thing is pretty simple. It would be pretty easy to simulate. Just have to mock the LCD and the control knob. And a lot of the components don't need to be mocked. EEPROM and so forth. The problems that we see in this seem to be logical, other than the flakiness stuff. They don't seem to be particularly tied to the target environment, so that that says maybe a simulator would be better. And also, this thing runs primarily with serial data, right? We've got the serial data channel going back and forth to the farm. It's really easy to simulate, monitor serial data on a PC. Much easier to work with the serial data than on the target. We can connect the PC simulator to an actual farm device for live data, or we can use text files of example data for repeatable tests, as we've already developed in years past for the farm. So we have example data sets to work with of traffic, aircraft traffic being monitored and reported by the farm. And it only takes a few days to write a simple simulator. We're not looking for a piece of artwork here. We don't need something fancy. We just need something simple to make it easy to run test cases and to debug. So, okay, well, let's save time. To scope the difficulty of building a simulator, the first thing we're going to do is try build the code for the Windows or Linux development environment. I'm not worried too much about the details of simulation just yet. Before we do anything else, though, what's absolutely required to be the first step in any project like this is to verify that we can build exactly the image of the last released firmware before touching anything. And this is really necessary to make absolutely sure we are working with the correct set of source code and tools. And I got to tell you, I've been given the wrong sources and tool chains more than a few times over the years, so check this first. What you want to do is set up the build chain with a comparison, ensuring that the results of the firmware build match the last hex file or whatever format you use for shipping the binaries of the application. And we're going to use this as we go forward because we're going to make some source modifications which are intended for PC only or to maybe clarify a few things in the application. And we want to make sure we get the same answer without breaking anything, so we want to automate that comparison as part of the firmware build. So we start to compile the code and look for trouble, and you will find some. Usually we will highlight problem areas. Just turning on all the compiler warnings will often surface a few issues. So you want to make sure everything compiles, but don't worry about linking just yet. That comes later. To get the thing to compile, we're going to have to stub out target-specific macros. So in this case, we have AVR macros for accessing the flash memories because it's not a linear address space on this chip. Interrupt masking and a few things like that. Not a lot, but you need to stub out a few things. The other thing you're going to need to do is comment out any ISRs. And for now, we're just going to if-def them out. Later on, we can segregate hardware-specific components a little bit more cleanly, but right now we don't want to make any structural changes that will cause the hex file compare to fail. So we're just going to comment them out with if-defs. And first thing we find out getting into this code is that there are bits of application processing buried in one of the ISRs. This is almost always a terrible idea. You want absolute minimal processing in ISRs. And ISRs should typically only post an event for processing at the application layer and do whatever minimal hardware management is required, but no application logic. We can see this is going to have to be moved out of the ISR and the ISR changed so it simply posts knob and buttons events. And this also will fix some potential race conditions because the logic that was in the ISR here didn't have any concurrency protection. We're going to identify code modules and interfaces where platform hooks are going to be required in mocks. So in this application, the LCD control, put pixel, instead of writing pixels over SPI to an LCD, it's going to write to an in-memory bitmap for rendering on the simulator GUI. Serial I/O polling from main loop will require mocking of the serial API, and the knob button input and time base to replace ISR. The knob and button inputs are just going to post GUI events, and from the application's point of view, it won't know that it didn't come from an ISR. The application processing will be unchanged, and the time base in this application will actually be able to be run in a real-time thread in the simulator. This always happens. Clean up the compiler warnings. You'll find always a few issues, some dubious code that will need some attention. And review the application control flow to make sure you understand how that's going to map into a simulator. So in this case, real simple because it's a super loop application. Now that we've scoped out the effort required and it doesn't look too bad, let's go ahead and try the first steps for this application and see what happens. So the first thing that we're going to do is symbolize some magic numbers. There are a bunch of magic numbers scattered around that are going to make the LCD management difficult in the simulator, and make it difficult to work on the application as well. We want to do that kind of change first because we can still run the firmware build and make sure that we have no changes in the generated code. So any kind of modification like that where you're trying to clarify something in the code without making structural changes, do everything that doesn't require structural change first and take advantage of being able to do a compare on the generated firmware. The next thing we're going to do for this application is move the application processing out of the knob and button ISR. We're going to, in this case, I had to segregate the event processing so that the ISR just generated some simple events. The application super loop already had processing to pick up and process events like this, so changing the ISR to generate event flags and changing the application to pick up the event flag was a very minor deal. This also fixed a rather serious potential race condition here because the application didn't have concurrency protection around the data structures which were modified both in the application and the ISR. We're going to create empty mock routines for target-specific functions that are needed to link. At this point, for this application, the only thing that's needed is the serial driver. So just empty mock functions for the serial driver API that's used by the application. And we'll add mocks for the knobs and button stuff and the LCD later. Now everything compiles and links, but it doesn't do anything. But what we can see is it'll be pretty easy to build a simulator. We've already found and fixed a race condition, and in a few days' work, we're already ready to think about building something that'll actually help us really continue with debugging and enhancing this application. And we've seen that it's really not hard. Let's review the control structure of the application, the simulator, and how it all fits together. First, the application is a classic super loop. And so what that means is each time through the loop, it's going to pull the serial port and process any serial messages into data structures. And the data structures are going to represent aircraft traffic in the area and any alarms such as a collision warning. Then we're going to pull the knob, the button, and timer events, and that may require some update of the GUI state machine. So it may be a menu selection, change page, that kind of thing. And if the data that came in from the FLARM or the user interface made any changes that require updating the LCD, then update the LCD as noted. So how do you put that all together in a simulator? In this case, the Windows GUI application is the main thread. We're going to run that GUI only. The super loop is going to be run as a separate thread under the GUI. It's possible in some simulation environments that you run the super loop one iteration per and the same thread as the GUI, but it's a little easier for this application to just run it as a separate thread. And also as a separate thread is the timer processing. Actually, it doesn't need to be a separate thread. It really doesn't matter. All that matters is that we're running it on a timer event in Windows as opposed to a timer event on the hardware. And that way the application is going to operate just as it does on the target, with things that rely on timing to function exactly as they do on the target. We're going to need to add a few events for diagnostics and simulation. Events need to flow in both directions between the simulator GUI and the embedded application. So what does that mean? It means when the GUI, when you press a button on the GUI, for example, simulating turning the knob to the right, we're going to simulate what the ISRs would do by posting events. The GUI is going to receive events. The application is going to have a few additional events added so that the application can notify the GUI simulator of diagnostics, so we can add debug messages, and also when it's time to update the LCD image on the GUI. And then we need to add some controls for the mocking of the serial port. And this will support either a real COM port connected to a FLARM or using file I/O for serial data. I should note that the WXWidgets framework makes it very easy to add custom event messages to the GUI queue. So adding events is very, very easy here. Let's get started and write the GUI simulator. I'm using Visual Studio. There's certainly lots of options here. You could use Eclipse and GCC. Some love code blocks. All the tools required to do this are free and some are open source. A few tips. I always like to start with a sample application that's very close to what I need. In this instance, we need a nice image of the LCD screen. So WX Widgets has a perfect example, which is the game of Go. And starting with that, it becomes very easy to build out the framework you need for the GUI. And then we need to add custom events, which also is very easy with WX Widgets for update the screen, update the LCD screen image, and for debug messages. The LCD routine, which is a driver that writes to the SPI OLED device on the target, needs to be changed so that when you do a put pixel in the driver, at the driver level, it updates a bitmap, and that bitmap has to be published so that the simulator can see it. And we also need to add a flag here where basically every time the low-level routine updates the bitmap, it sets a flag saying the screen has been updated. And then at the end of the super loop, we'll add an additional message. So if this flag is set, we'll push an update the screen notification to the GUI simulator and clear the flag. And for now, we're going to mock the serial port just with some diagnostic messages. So when the application sends data or sets the serial port properties, just push a debug message for now. We're going to mock the EEPROM so that it pretends like it's empty. Just return FFF whenever there's a read operation. And you should note here that very, very, very minimal application changes are required to do the above. We're talking about a dozen lines of code. So where are we? You can see the splash screen comes up and start the application. Let's have a quick look at the screen here. We have some buttons I've added to simulate the events, depressing the knob and releasing the knob, turning the knob to the right, turning the knob to the left, or clockwise and counterclockwise, pressing with a short click, pressing with a long click, and some controls to manage mocking of the serial port. So what happens here? We start the simulation, the thing comes up, it's alive, puts up the splash screen, and you can see it's actually here in the debug window I've created. The mocked COM port is showing us that it's sending out hello messages trying to configure the FLARM communication port, and it's going through an autobaud process, so you can see it trying to connect at various different baud rates. So it's up, autobaud starts. This is after about 6 days of effort. So we have a simulator with less than 2,000 lines of code, a lot of which is GUI boilerplate that came from the sample application. And it's already up and running. We've already fixed a few latent bugs, the race condition we've talked about, and some coding issues. And so, it seems like we're in pretty good shape to proceed with the update of the FLARM protocol and adding the new feature. And as we say, what could possibly go wrong? Now that we've got all that out of the way, let's hook up the serial port, both real and simulated, and start work. So what happens? Whoops. Immediately, subscript errors are caught in the debugger by the Visual Studio built-in array bounds checking. What happened? The LCD was being written out of bounds and there was no checking in the driver. And this is probably the cause of some of the screen artifacts that we've seen in the application. So obviously some work is going to be required. But this is the most important point perhaps for this area. The PC tools have bounds checking that's typically not available on a target system. And that includes things like GCC Sanitize, the Visual Studio bounds checking. Eric Steiger has done some work porting Sanitize to the ARM embedded target, but the resource use of these tools is very high. And such resource use is no problem for a simulator, but it's often impossible on the target. Okay. So we add some asserts in the LCD driver, track down and fix various bugs that are causing the thing to write beyond the boundary of the screen. And what happens next? Another subscript error caught by Visual Studio's built-in out-of-bounds checking. So what's wrong with this code? Have a look at this. We're checking selected alarm, which appears to be an index, against what appears to be a magic number here. As long as it's not the magic number, we're doing something here. But oops, we're dereferencing the magic number. That's extremely problematic. When magic numbers are used for subscript values, they always lead to errors like this, and this would have been caught in a code review. So that's a very, very important takeaway here. You see something like that, whoops, guess what? No code reviews were performed here. The worst thing about this is that in this particular instance, we have a read reference. But look what we're doing here. We're taking the alarms array, we're dereferencing it to get a pointer, which we're then referencing. Okay, so here we're reading from a random location in memory. But unfortunately, this same pattern occurred in a number of places where it was writing to the pointer, not just reading. And so guess what? That's likely the cause of some of the memory corruption that's suspected to have caused things like one of the options disappearing during operation. When you find problems like this, it means you really need to do a serious sit down and review the code. As old Chinese proverb says, there is never only one misspelling on the Chinese restaurant's menu. And try it sometime. If you find a misspelling on a Chinese restaurant menu, I dare you to send me one that only has one misspelling. But a serious error like this, again, means no code review is performed, and that means that it's going to be needed in this case. So time to start reading the code and looking for trouble, because having found one spelling error, we know there are going to be more. What's wrong with this code? I wish we had the opportunity to do this live. Anyway, you can see that X isn't protected with parentheses in the macro and the macro definition. And in this macro, you get the wrong answer because of X not being protected by parentheses. In this application, that actually led to a miscompare. The application orders the target aircraft by distance, and it was ordering them incorrectly because of this problem. So you need to always wrap your macro arguments in parentheses, but even better, use a C++ inline template function so that you can't have this kind of mistake. Continuing with the code review and some cleanup work. You want to make sure that you comment anything that's not immediately clear at first glance. You don't want to have to figure out a second time or a third time, and you're going to have to be coming back to this code. So as you do the code review and you can't figure something out, make sure it's commented clearly. And address anything dodgy. So in this application, I had to refactor some cut and pasted enemy A parsing code that occurred in a few different places into a nice clean C++ class. Then I found this. What's wrong with this bit field in a structure, which is also updated by an ISR? Bit fields are not atomic operations on many machine architectures. In this case, the AVR, if the main line is doing this operation here, decrementing the value, you have first a load operation. Consider the main line does the load. Then the ISR fires, and it goes and it updates a different bit field in the same word. And then the main line resumes, and it does some operations, and it stores. Well, that race condition just erased the value update that was performed by the ISR. So bit fields, they're not atomic. They cause race conditions like this. They take up a lot of space. And in this case, getting rid of the bit fields saved 1.5 KB of flash and cost 22 bytes of RAM. So don't use bit fields unless you have a very good reason. Okay, I keep saying this, but finally it's time for the real work. I don't get any more subscript errors paging through different display functions. Everything seems to be basically working. I seem to be standing on slightly more solid ground. So, first thing is update the protocol to the current version. Did that. And the first thing that happens here is the startup report. You get this little report of the FLARM software version, things like that, when the butterfly display is first connected to the FLARM. And it fails intermittently when connected to the FLARM. And the interesting thing here is it fails on the simulator intermittently. And the reason for that is there's a coding error where the code was unnecessarily dependent on the exact timing of messages. But because the actual timing of the timer ISR is correctly simulated, the symptom appeared and could be fixed on the simulator. Okay, so fixed it on the simulator. Next, add the new feature. Menu item that sends a request to the FLARM and displays confirmation from the FLARM. And this worked fine in the simulator, but when I put it on the target, I build the embedded version and put it on the target. Sometimes it fails, depending on the level of traffic. So, okay, what's different in the simulator and the actual target here? I mean, the code is the same, the application code is the same. So what's the difference? The difference is that the PC has very deep buffering for the serial data. So let's have a look at the target. We can see that we must have some drop messages, and the application, unfortunately, didn't have any checks. Remember, we talked about this at the very beginning. You need to be paranoid about this stuff. You need to have checks to make sure there's no data loss. If the incoming data buffer ever fills up completely, you're losing data. Okay, so I added some diagnostic information to the embedded version, and what do we find? We find that the diagnostics on the target confirm that the buffer is overflowing and we are losing NMEA input data. Thank you, Robert. So let's have a look at the driver. It's an open source AVR serial driver, and guess what? A couple of bugs. There's a 1024 byte buffer, which really seems like it ought to be enough for a pretty fair amount of NMEA data, but it's indexed by an int 8. So of the 1K that was allocated, only a quarter K was actually used. And there were 2 race conditions in the driver. Okay, fix the driver code, put it back on the embedded target. But you have to think a little bit more about this. Why was 256 bytes inadequate? Going back and reviewing the code, application performance bug here. Potentially the code was updating the screen, the LCD screen, after every message. So every time there was an NMEA input message framed and processed, it went through the super loop. But for a device like this, the screen update is extremely slow. It's not a very fast processor to begin with, and we're trying to update a very large number of pixels on this graphics screen in color. There was also no diagnostic timing in the application, and so there was no easy way to see that this was happening. Okay, fix it. So first, process all the queued message, which is pretty quick compared to the screen update, and then do the screen update. And guess what? It doesn't overflow anymore. This is a really important point here. This is the very first bug of all of the stuff that I've fixed here that required the target hardware to observe and diagnose and fix. And this is very typical for a lot of embedded applications. Most of the problems aren't related to the target. If you have an application of this style and complexity level, the target has very, very little to do with the application performance. And this is why a simulator is so much more efficient than debugging on the target. Another quick point: using an RTOS with prioritization of the processing would have prevented the bug. It does introduce some additional complexity in that you would have had to have locking around the shared data structures. Here's a quick example of how this all works together. Let's connect. We're going to use a file input. And let's choose hell of a lot of aircraft. And start the application. And this is a really long script, so we're going to skip ahead here. Now we see an aircraft approaching from the front, and shortly we'll get the collision warning. I didn't mock the beeper in the simulator, but at this point in the cockpit it would be screaming bloody murder, warning you of a collision hazard with an aircraft dead ahead and slightly higher. The firmware was sent out to a few customers for flight test, and there were reports of sporadic failures of the ID lookup. FLARM uses a 6-character hex ICAO ID for a unique identifier for aircraft, and the product has a database. This display product has a database of known aircraft to present a more user-friendly identification. What's wrong with this code? We can see the ID was stored as a character array and periodically converted from the string to a long base 16 here. But if you look at this code, there's no terminator here. And 22 out of 256 possible values are valid hex digits in ASCII. So the lack of the string terminator causes this to sporadically return the wrong value. Access beyond an array like this embedded in a structure is not picked up by the Microsoft tools nor any tools that I'm familiar with, not Valgrind and not the Google tools. So that's a rather difficult one to find. This one was again found by inspecting the code, because it mostly worked, but sometimes it didn't. So how could that happen? And changing the code to just always store the converted value rather than the character array shortened the code and fixed the bug. If you must have elements like this, where you need to embed an ID and carry it around, wrap it in a class and consolidate all access and conversions. This code had numerous places where it was doing string comparisons, mem copies, and so forth, and all with hard-coded lengths. And that's really asking for trouble. The purpose of this exercise was to show what happens in a real-world typical embedded project, and not to show what Dave did during his summer vacation. So let's have a look at the statistics of what actually happened for the top dozen bugs that needed to be addressed in this project. First of all, 6 of the problems were found by studying the code, by inspection. 4 bugs were found and fixed in the simulator, and only 2 required the target. Only 2 were not reproducible on the simulator. To point out again that most bugs were found by inspection, the most important thing here you can take away from that is you need to do code reviews. This stuff would have been caught with decent code reviews, and it's a lot less painful to catch it up front than to find these problems and fix them later on. Again, many of these were found and fixed in the simulator, and some were only possible with the tools on the PC. You can't do some of the things like the array checking that were performed in the simulator with the tools that are currently available on the embedded target. Only 2, again, required the embedded target. None required the embedded debug. I never did hook up the embedded debugger. There's no embedded debug for this project. Everything was done on the simulator. The flaky behavior, the memory corruption, which was found and fixed, would have been extremely difficult to find on the target and was quite easy to find on the simulator. Let's recap some of the lessons we've learned. We reviewed a very typical embedded product. This is the kind of thing you're really going to encounter in the real world. And the coding of this product was actually a bit above average, but nonetheless we can see that a few things which are very common. First of all, skipping the code reviews really hurt here. Lots of the bugs that were tracked down and fixed during this project would have been caught with proper code reviews, and it really helps to find the problems early. You save a lot of time and aggravation and cost to do it that way. A quick and dirty PC simulator really helps. And this is even for an existing project and a relatively small project. The simulator took maybe 7 days of work, and it saved a lot more time than that by speeding up the development that was required. Few of the bugs you're going to encounter in the real world actually require the target. For many classes of applications, most of the bugs have to do with logic errors and are not specific to the target. A simulator facilitates scripted testing, and that saves a lot of development time. This simulator only uses a serial data stream for scripting. We're just feeding in the enemy A data stream. But it would be really easy to add complete scripting with events. So, for example, to be able to, in that same stream, simulate pressing a button or turning a knob or time delay. And that would provide complete regression testing and support continuous integration. Very easy to add. When in doubt, use a simulator. And when you think you don't need to use a simulator, use a simulator. The manufacturer of this product once thought that simulation didn't pay off, and they now use simulation for all product development. You need to put good diagnostics on your targets. You got to check for drop data, filling up input buffers and things like that. You have to check memory use. You have to be able to also monitor performance and make sure you don't have problems. In this case, the performance problem would have been easily noted by noting the data overrun. And I want to make a special thanks here to the manufacturer of the product for allowing me to use all this material, and to the numerous people that helped field test and get this product all sorted. So thank you very much, and we'll proceed to questions. We had a great Q&A session after the lecture at the Online Embedded Conference. Sorry you weren't able to join us. Hopefully you will be able to join us next year. I made this quick recording recapping some of the discussion we had. First, I should clarify: the FLORM traffic and collision product produces a serial stream of data about the traffic that it sees. A lot of the FLORM products don't even have a display. This product is just a display product which listens to the FLORM serial data stream. Sorry if I didn't make that clear. Okay. So first question: why didn't users notice drop messages? This is kind of interesting. FLORM is continually resending data about the traffic that it sees. And the display products don't stop displaying a target unless they haven't received information about that target for some period of time. So what happens is, if you drop a few messages here and there, you're not actually going to be able to tell as a user. If it would have been more obvious, I'm sure these problems would have been fixed years ago. But because of the way the system works, it's not immediately obvious to the user if you lose a message. Next question: who is that handsome bird who just flew away? Rupert is an African gray parrot, and he's got about 20 years coding experience. Next question: could static analysis find any of these problems? Theoretically, 6 of the 12 worst bugs that were discussed could be found by static analysis, the others not. I contacted Perforce for the Clockworks product and also Coverity, but their salespeople failed to call back. And these tools are completely useless if you can't get them, and you can't get them at a reasonable cost. Coverity is freely available on GitHub for open source projects, and that may be a very good tool, but not helpful for proprietary projects like this one. I did try the open source CPP check static analysis tool, and it only found 1 of the 6 potentially findable problems. So helpful, but not hugely helpful. Next question: where can I find resources to write a simulator? First of all, a lot of the tools that you can get, the RTOSs and such, include versions that run on Windows or Linux. So FreeRTOS includes a version for Windows and a version for Linux. QP includes and recommends that you start with using their simulator. And adding a GUI framework on top of, and some rudimentary scripting to control it on top of, for example, FreeRTOS for Windows is really only a few days' work. Nothing very remarkable there. Next question: can you share the simulator code you wrote? The application we discussed contains proprietary software. That's all proprietary. If you're really interested, send me an email. If I get enough requests, I'll make a skeleton of the simulation framework with all the proprietary bits removed. Next question: I've done PC simulation for years. Why is this so surprising to many developers? I feel the same way. We've done this for more than 30 years, so this is not new and novel. And I also worry when folks find it surprising to talk about simulation of these applications on a PC or any kind of host. Many MCU and toolchain vendors don't emphasize simulation or even talk about it. And not enough of them emphasize any form of automated and repeatable testing, which is also a worry. And I think another factor is that simulation is often missing in some of the education that's offered for embedded. Next question: what about speed? PC simulation can be slower or faster, and it's not going to be timing accurate. That's absolutely true. Two-part answer to this question. So firstly, most bugs are not timing and synchronization related. They certainly happen, but they're not the majority of the things that need to get shaken out. The second part of the answer is that some simulations require control of the time base. So your simulation script would control the time base. In this application, the GPS data coming from Flarm could be used to directly control the time base of the simulation, so it would run faster than real time. But in any case, it's not going to help you if you have timing and synchronization bugs. That's a little bit tough to catch in simulation. Next question. Decoupling hardware components seems hard. Again, if you can't mock a component easily, you've probably got a design error. And it could be something like we saw in this application, ISR containing application logic. But if you have proper abstractions, it should be pretty easy to mock. Okay, next question. Steve's presentation talked about NASA's simulation for the Mars mission. And after looking at that, what can you tell us that you found hard to simulate? I got to tell you, Steve's talk was fabulous, and I personally want a simulated pyrotechnic device for my desk. I guess they had a lot of pyrotechnics in that mission. It's interesting. Footnote before we answer your question, it's really, really important to segregate components as they did, as he talked about for the Mars mission. Okay, the simulation. It took a lot of resources to do all that simulation, but creating and debugging an application like the Mars mission would be really foolhardy without simulation. What folks generally don't understand is that for a similarly complex commercial application where failure might be considered acceptable, it would still be less expensive and less time-consuming to build the application with simulation. To your question on difficult to simulate components, and maybe to clarify again the previous answer to the previous question, we're not trying to simulate on the PC low-level hardware like a DMA controller. We're trying to simulate the sensor result that's read by the DMA controller. That's the interface that's mocked. And so we typically don't have problems simulating components because we're choosing a level of abstraction that makes it pretty straightforward. Next question. I work in a tiny team. What if there's nobody available for code review? That's problematic. When I'm working on personal projects by myself, what I do is I set code aside for a few days and then I come back to it to review it. And what you got to do when you're looking at code like that is you got to ask yourself, is this code I would be happy to receive? And invariably, there are going to be places where you need some better comments, variable or member names need improvement, and you're going to see that kind of stuff after you put it aside and come back to it. But there's really no substitute for a qualified second set of eyeballs. You really want a second set of eyes checking stuff because you can pick up a lot of problems that way. Next question. Can you say a little bit more about the Google's ASAN sanitizer and its limitations? So, okay, ASAN is available. It's now available in the Microsoft tools, and it's been available for quite a while in GCC and CLang. But it's primarily about management of free storage with malloc and free. So, did you reference beyond a block that you allocated? Did you free a block twice? Did you reference a block after you freed it? It's great for finding those kind of problems. But it doesn't have array bounds checking, as is built into the Microsoft tool. And in many cases, for a lot of our embedded applications, we don't use malloc and free. We might use them for like if FreeRTOS, if you're not using the static allocation methods, you use it at the beginning to set things up. But you're really not often using malloc and free a lot in an embedded application, we hope. So I'm not sure that these tools are really applicable, and in any case, they take resources to a degree that you may not. It would be very common, like this application. There's no way there are enough resources on the target to support those tools. So I'm not sure they're the best tools. If you are using malloc and free and you're using a simulator, okay, then these are going to be helpful, but not on the target, I don't think. Eric Steiger's got the stuff running on targets, and if you go to MCO on Eclipse, you'll you'll find his website. You'll find a write-up about that. But I think it's not the best set of tools for embedded, at least not the low-end embedded stuff. So with that, thank you very much for your time and attendance. I hope you can join us next year when we do the next embedded online conference, and hope to see you there. Thanks again. Take care.